Okay, thanks everyone for joining this webinar. Thanks for making time to attend this webinar. Um, so my name is Steve Kang. I'm the Senior VP of Engineering here at QualityLogic. With me is John Lunsford. He's the, many of you know him, Fax Technical Lead and the instructor, and he'll be the person demonstrating DataProbe 3.0. So I'm going to go through some few slides to give you an introduction. And here's the agenda for the webinar today. I'll give you a brief introduction about our fax testing tools, and then I'll hand it off to John Lunsford, who will go over fax over IP and how to deal with fax over IP issues using DataProbe. And then we'll wrap up final 15-20 minutes with any Q&A. Some of the tips for the webinar, please post any questions using the webinar's questions panel at any time, and then we'll save those for the final Q&A section to go through those. And then all of you are muted, so you will not be able to speak on this webinar. So as many of you know, and some of you don't know, the FaxLab is our interoperability test tool. It's a native Windows application that has software and hardware, custom hardware, and it provides real-world emulations of over 170 fax machines. So what that means is, our product, our test tool, fully emulates the T30 behavior of these devices, including any anomalies that the particular device behaves. It's a very broad fax interoperability testing tool, and it gives you very broad coverage, and also gives you ability to create in-depth T30 call type selection. It's really ideal for automating fax testing for both over IP and analog channels. And finally, it gives you also remote control automation ability. So if you have a particular automation framework, we give you the APIs to hook our FaxLab engine to, so you could control that from your automation framework. FaxExpert is a tool that's really designed for advanced users who have in-depth knowledge of T30. It gives you ability to fully program a T30 fax message on the fly, and it also gives you ability to create test cases on the fly using our Windows application. And then also we provide consulting and also testing services, as well as training services for companies. Not only train you in fax technology, but we also assist companies in analyzing T30, T38, G.711 interoperability issues, and do that in your network as well. We've assisted many companies in resolving these fax interoperability issues, and the service could be performed both on-site and also remotely from our company as well. And then finally, the star of the show is our DataProbe 3.0. It is an analog and digital fax transmission analysis tool. We perform both analog and digital fax transmission analysis, including T30, T38, and G.711. The G.711 analysis is now introduced in the new 3.0 version, which John will demonstrate and also explain further about. Our tool provides full conformance analysis by analyzing the signals that's going back and forth, and also gives you a convenient end-to-end and ladder diagram, starting with the original T30 signal, and which also gets transformed into the digital T38 and G.711. Our tool gives you live analysis and capturing capabilities, so you could tap analog or digital line, and we'll capture the traffic, and we'll also analyze the signals. In addition, you could import the PCAP and WAV files that have these signals captured in it, and we'll do an offline analysis for those. So we have two products available. T30 is the analog version of it that does T30 analysis. And the T30, T38 analyzer, which is what the product is called, we'll do a native analysis of both T38 and G.711 exchange. So with that, let me hand it off to John Lunsford. He'll give you a explanation, also a demonstration of the DataProbe version. John, take it away.
Good morning, good afternoon, and good evening, wherever you are in the world. My name is John Lunsford, and as Steve indicated, I do a bulk of the fax tech support for QualityLogic. I was also instrumental in the creation of our fax test products. Basically, DataProbe is intended as a protocol analyzer. As Steve mentioned, it comes in two flavors: the basic T30 version, which absorbs and looks at analog RJ11 signals commonly sent over regular telephone systems via switch circuit, which is actually what facsimile was designed for. Since much, if not most, of the telephone traffic in the world is now going over the internet, we found it necessary to expand DataProbe to cover such subtopics as T38 and G.711, so that we could also look at fax messages that were going over the internet. The two versions are complementary. The T30, T38 version obviously includes the T30 version, so we'll just address DataProbe T30, T38 and cover both options. Again, DataProbe is a passive monitor that captures fax calls. What this means is that it will literally listen to the communications between a fax terminal and its connection and absorb the analog signals going back and forth between the terminal and its remote terminal, and also analyze these for T30 content and present that information to the user. It operates by version of having software that lives in Windows and performs the control of the monitoring process, the storage of the data, and the analysis of the data. It also operates a device called a data trap. The data trap is a piece of hardware that is the physical collection system that sits between the terminal and its connection and absorbs the analog signals going back and forth. The data trap also acts as a call control. It is literally sitting there listening for the terminal that's on that line to go off hook. When the terminal goes off hook, then the data trap starts to record. T30 protocol analysis is fairly straightforward, but it's very detailed. So we're going to look in that in some detail when I actually get to the point of talking about DataProbe itself. It supports the full array of modulations, encodings, resolutions, and all of the other varieties of differential information between the different fax transmissions that are available via T30 today. We actually cover quite a few modulation resolution combinations that no one appears to be using yet. We have multi-node configurations available. DataProbe is capable of supporting technically up to 128 data traps. We've never tried that many before, but we have gone up to 32 to monitor a full E1 line. By and large, fax calls tend to work without issues. That's one of the reasons why it's stayed around so long. The principal problem with it has been not so much the idea of being able to get the communications, the modulated carrier signals across the carrier lines, as much as it has been interoperability between terminals. Unfortunately, T30 was written with a very loose set of specifications, the result of which has been that many manufacturers have been very creative in their interpretation of those specifications. And the result has been that you can have two fax machines that both completely obey T30 that cannot talk to each other. Literally, they will never exchange pages. And so part of what DataProbe is used for is the discovery of and resolution of device interoperability issues. Now then, you may be sitting there thinking, so what does all this have to do with fax over IP? Well, for a fax to go over the internet, one of the first things it has to do is go through a gateway that takes the modulated carrier tone and turns it into packetized digital information. That gateway effectively becomes another fax terminal because the originating terminal is talking to its gateway as though the gateway were the answering terminal. The answering terminal is talking to its gateway as though it were the originating terminal. So you have two T30 implementations in the gateways themselves that have to be functional and interoperable with the terminals that are talking to the gateways. So you begin to see some of the complexity that enters just the interoperability level of the process. A basic connection diagram for DataProbe itself is what you see here in the diagram before you. DataProbe itself runs in a host PC running Windows. It is a Windows-based system that will operate the data trap. It will control the process of configuring the data trap, effectively arm it, if you will, to begin monitoring and then receive the data that it collects. The data trap monitors the actual RJ11 analog communications between the fax terminals and the PSTN or other device that they may be connected to. Now, a point to recognize about this is that DataProbe is listening to these communications. It in no way, shape, or form influences them. Its purpose is to be a transparent monitor. So it will record whatever goes on between the two fax terminals and report it back to the host PC. You'll notice from the diagram that our preferred use of DataProbe is to have two data traps, one at each end of the call. That way we can compare what happens at both ends and allow for whatever disruption occurred over the PSTN network or possibly over an IP connection that runs off of that. So what happens when you send fax over IP? Well, unfortunately, a lot of things. To start with, fax as defined by T30 was intended for a switched circuit network. The point of that being that the network was an analog signal carrying system. It was completely intended to be operated as a closed loop. Literally, the two fax machines were sitting there talking to each other over a effectively single loop of wire, even though it might have been interrupted by a microwave link somewhere in the middle. The point of this is that fax has built into it a number of corrective processes, a number of error correction and avoidance schemes that were specifically designed for the PSTN. It has timing controls, it has modulation verifications, it has several things that are specifically intended to deal with the sorts of issues you get from the PSTN, such as signal delays, distortion of both amplitude and phase, noise, typical things that you have in dealing with transmission of analog signals, which actually works fairly well for the PSTN. Again, when you get into interoperability issues between terminals, things can go poorly. However, when you've got interoperable terminals, PSTN tends to be a good carrier for fax. But when you take those signals and go to put them into data frames and send them over IP connections, you come into a whole different set of problems. Because the internet has issues with things like misrouted packets, dropped packets, and jitter, where packets arrive at odd times. And fax is looking for this continuous stream of analog data. So T30 itself has nothing built into it to deal with this. And the result is that when the fax signals are converted to go over the IP network and then reconverted back into fax signals, you have to compensate not only for the analog ends, but also for the digital middle, if you will. IP networks use various transport and encoding protocols to try and get around this. The other issue that tends to come into play with fax going over the IP network is the fact that many IP networks do multi-hop arrangements. They will go from one of these protocols to another in the process of sending a fax, and transition between protocols is one of the places where the issues tend to appear. DataProbe 3 has brought into the game the capability to monitor the G.711 protocol for sending fax messages over IP systems. And a brief discussion of the distinction of G.711 versus T38, the other typically used protocol, is in order here. T30 is a series of data messages, either control or actual transmitted page data, that are sent one at a time over a PSTN circuit, and they have specific time delays placed between them, specific structures and content, and it's a half duplex system. You send one way, then you send the other way. To do that over an IP system, you have to do kind of basically one of two things. Either you have to extend your analog connection via digitizing the signal one end and then integrating it again at the other, or you have to take the T30 messages and in some way turn them into data IP messages and then turn them back into T30 at the other end. Option number one is G.711. It was one of the first voice over IP protocols that was used to transfer voice calls from one end of the internet to the other. G.711 pretty much does just exactly that. It sits there and digitizes information into a stream of packets that are then reintegrated at the far end back into an analog signal. This is really kind of an idea that looks like it ought to work really well with fax, but again, due to the fact that it's going out in packets of numbers, has the problem of what happens if one of those packets disappears. G.711 has no capability to compensate for that. So there is the issue of what goes on when the internet itself gives you the effect of having dropped a piece out of a call. Fax handles that very poorly, and in most cases not at all. If you lose a G.711 packet, you'll lose your call. T38 was an attempt to compensate for that by taking the T30 messages and turning them into digital IP messages in T38. So each T30 message has its T38 equivalent. The message transition is sent across the internet and then turned back into T30 at the far end. Typically, it makes for a more reliable method of transport. However, G.711, having been there first, tends to have the lion's share of the transmissions, just simply out of the fact that for a lot of gateways, it's the default method of transmitting fax. Number of operators are becoming very savvy about all of this and will go in and directly tweak for either T38 or G.711, depending on what they're dealing with in their particular networks. DataProbe, in order to analyze all of this, goes out and watches IP data to look for SIP sessions. Session initiation protocol is probably the dominant method for making IP data connections now. And those message pipes are established for sending messages both ways through the system. So a SIP session sets up a connection between gateways that then talk to their individual terminals. DataProbe observes and recognizes the SIP sessions. It records and reports back all of the fax over IP packet information that's going on. That information is then analyzed and turned back into T30 messages within DataProbe itself. That gives us the capability to look at, okay, what happened at the terminal? What kind of T30 messages did it send? What did the gateway do? It either generated G.711 or T38 packets. When we turn those back into T30, do they match up with what the terminal did? To do this, we relate the IP traffic to the PSTN traffic with what I call a ladder diagram. Literally, there's a diagram that in one column says, okay, here were the T30 messages from the originator, and the column next to that, here's the set of IP messages, be they G.711 or T38, that came from that. And the next column here is what was received at the answering device. And when the answering device responds to control messages, it traces the path back the other direction. T38 and G.711 are both subject to their own peculiar idiosyncrasies in terms of what they do to make these conversions. Since we are looking at basically a two-ended transmission system, what we try to do is provide the capability to look at the analog signal with the data traps, and then we actually directly tap into the IP connection using a network interface card in the DataProbe host computer. So that gives us a capability to look at the entire process. One of the things we did with the data traps was we made them operate via control and data transmission over TCP/IP networks. So literally you can put your data trap any place where you have an RJ11 signal to listen to, and you have an IP connection that can go out and control and access the data trap. We can do multi-node configurations, as I mentioned earlier. We've even done full E1 connections. Now then, wonderful as all of this is, there are times when you can't use the data trap to go out and record your analog signal, and you don't have the option to directly get into your IP network with your DataProbe host connection at the time the call is being made. Howsoever, there are commonly systems put together that have the capability of recording WAV files for the PSTN information and PCAP files for the IP information. WAV being one of the common Windows recording of analog sound files, and PCAP is the output of Wireshark, probably the most common network analyzer. So what we can do is we can import these files and match them up as though we had recorded them ourselves. Literally, we can take a WAV file, we can analyze it, extract the T30 messages, we can take a PCAP file, play it back, and pick the either G.711 or T38 messages out of it, and again compare them against each other in that ladder diagram I mentioned earlier. Typical connection arrangement for doing what I just talked about, it's on the screen here. Basically, you have the host running DataProbe, goes out, controls the two data traps. They are listening to the front ends of a pair of gateways. Literally, whatever comes over the PSTN and goes to those gateways has to go through the data trap for monitoring. You can see the two fax machines are operating through the PSTN, going into the phone number that connects to the gateway, and to do so they actually go through the data trap and watch the input at the gateway end. We also have a signal pickoff between the gateways that comes from the IP data, goes back over to the host, which is where we're listening to G.711 and T38 information. This is probably one of the more common schematics for use of DataProbe, in that you listen to both ends of the call, looking to find out what happened at each end, and then backtrack that to any kind of disruptions that occurred in the connections. Okay, let's look at DataProbe itself now. This is the main DataProbe screen. The process that DataProbe uses to record and analyze information is that it operates the data trap, goes out and listens to the IP connection, and records all of the incoming information into a database. It uses an index into that database that indexes all the information by calls and by T30 call signals. The top level of that index is what you see up here at the top of the screen. This literally is a call list. It has a list of every call that has been monitored. It gives you the ability to put your own information on it, to tag it for whatever particular test information you would like to put on it. You can put, I believe, up to 128 characters in the name, although that makes kind of an interesting display up here. But it gives you the capability to identify each call and looks at a result versus T30. This result of passed or failed is going to look basically at, did the call obey T30 in the large sense? And by in the large sense, I mean, did it obey it enough to complete the T30 path? All of the messages were exchanged with each other. The violation of the parameter limits in T30 is so common that it actually becomes a distraction if you try and use that as an analytical tool. So we'll tell you what the parameters were, if they were violated, and by how much. But for the most part, what we're looking at for pass-failed indicators is, was the call successful? Did it manage to get all the T30 messages exchanged and pages went across? Of course, we date and timestamp each call, identify its source, whether it was coming from a data trap or whether it was coming from a tap into a T38 or G.711 IP data stream, show the answer and originator phone numbers that are sent with the call, and then apply our own unique ID number. As an example of the data that we show, I just selected this top message up here, and now the call summary appears. I have a set of tabs I can select across the bottom, and the call summary is just that. It's showing a summary of the call map. These were the T30 messages that happened in this PSTN call. Now again, this is not looking at the IP portion of the call. This is looking at the PSTN analog portion. It's showing all of the messages that were exchanged, the tonal messages that basically indicate that this is a fax call, the control messages that determine how the call is to be exchanged, and then the exchange of the actual page data and its confirmation at the answering device, all the way down to the end of the call, which completes with a disconnect message. We give you some information about this. Your answer and originate phone numbers, some of the data streams that were exchanged, some basic information about the page data that was exchanged, and especially in ECM, the error correction mode, will tell you how many frames had frame corruption problems, how many of them had to be retransmitted, and that sort of thing. Then we do a very quick analysis in the summary, which talks about literally how successful was the call. Did you exchange the pages? Were there any bad lines in the pages? What happened? Which device were we monitoring at this point? Are the originator or the answerer? Things of that nature. Okay. This is the summary information that is a compendium of what was recorded in the database for this particular call. It's useful for being able to quickly survey the calls and say, okay, that one I'm not interested in, that one I'm not interested in. Oh, this one had something strange. That I want to know more about. When you get to that want to know more about portion, then you use our detailed view. Detailed view comes down and shows you the actual detail information for each one of those T30 messages that I mentioned earlier. Literally, you can select these individual messages to get further data from the message itself. Very quickly, let's look at one of the control messages here, the DIS, which sends the capability message back from the answerer. And you can see that there is a variety of information shown here about the structure of the message itself, the HDLC frame design, the data streams that were in it. We can look at the data in the structure, the individual bytes that were used. We can identify the bytes and tell you what each one of them was. You can see if there was a frame corruption here, if the 70 flag stream had a hiccup in the middle of it, all manner of such things. We provide this for low-speed control messages. For high-speed signals, we will show you, again, a set of characteristics about them. We can show you the raw data. Here was the training signal, which you can see had a little bit of issue because there was some garbage up at the front of it. But again, it wasn't anything that stopped the call, wasn't anything that prevented the transfer of pages. For partial pages, we can display similar levels of information. We also have the capability to show what we call a PDSNR analysis, as post-delivery signal-noise ratio. The point of this is that while this is not a direct modulation quality measurement, we don't do a bits per million issue or anything like that, but what we do show is our ability to parse that signal out of the PCM information that the data trap saw. We also will do this with an imported WAV file. So it gives you a good idea of, okay, was this a well-formed set of modulation symbols? We saw a good representation of the call, or were these things kind of messed up? Was this a case of there was some distortion happening in the system someplace that was affecting the analog T30 end of the call? Now then, in addition to that, we have the capacity to look at two different varieties of IP data. First off, we actually look at the voice over IP signal information and break it down into the signals themselves. This is a G.711 call, and you can see it starts off with a SIP exchange to set up the call pipes. It then goes over to RTP, the real-time protocol, to do the G.711 exchange. And then it has, let me get this out of the way, a whole array of the messages that are exchanged via RTP. Literally, these are your G.711 messages, and if you wish, you can directly look at this same information with Wireshark. We'll export a PCAP file that has this in it. You can look at it from Wireshark to see what it has to say about the network exchanges. You can look at it with DataProbe to see that the actual information was being exchanged for the fax call. What was contained within this is a G.711 call, which again was digitized analog data containing T30 messages. So we also give you the ability to look at it as just that, a set of translated T30 messages. This is that same call that you just saw that just had all of the fax over IP information flowing back and forth, but this is the interpretation that a device would see if it took that back into an integrated analog signal and poured it into an answering device. So here, once again, are your different signals. And again, we provide the same set of analysis information as though we had captured them from the analog ports themselves. With G.711, when you're capturing the data, there is this interesting situation of the fact that the originator and answer are actually sending separate data streams. So part of what we have to do with this information is to take those two data streams and lay them over each other again so that we can present you the entire call as a series of answer originate messages. And G.711 has this interesting dichotomy wherein it can either send you a stream of data, it's just one long round of packets of sound data, or it can send sound data and then silence, and then sound data, and then silence. And when it goes to mode number 2, it's a little bit of a challenge to directly recognize what the silence parameters are that are being specified in those packets and make sure that you get everything aligned again. Okay. We also have the capacity, as I mentioned earlier, to look at T38. So let's quickly look at a T38 call here. That's what this second round of call information is towards the bottom. Again, we have fax over IP information, and you'll notice that it starts off with RTP in order to exchange those analog signals that determine whether or not you indeed have a fax call. Once the fax call is determined, then for T38, the gateways have to switch over from carrying RTP analog signals to UDP-TL, which actually has the T30 information in it in T38 packets. So this is the T38 information. If I select one of these, you'll see this is the packet traffic that carried that particular T30 signal. and it's in a whole array of packets, because one of the things T38 does is it applies a granularity filter to try and break the data up as much as possible and avoid network congestion. So one of the things that's probably somewhat interesting at this point is let's look at those ladder diagrams that I mentioned earlier. Let's go up and select our PSTN, our G.711, and our PSTN answer, and look at our end-to-end analysis. And this is what I was mentioning a moment ago. Literally, I have picked off the analog origination, the analog answer, and the G.711 IP data that exchange information between those two. And again, you can see the information flowing from the originator through the G.711 data and into the answerer. And as we scroll down the other direction, you can see, once again, here's training coming down and CFR coming back, the partial page, the post message command, and the MCF being returned. So again, you can trace the exact process through the originator, IP connection, answer, IP connection, originator. We also provide some information for each one of these signals so that you can quickly look to see what the status of the signal itself is. Is it basically doing what it's supposed to, or does it have issues? In addition to being able to do this for G.711, we also have the capability to do this for T38. And with T38, again, we do the same thing. We pick up PSTN, the SIP pipe for T38, and the PSTN answer side, and again show you all of the information going back and forth that shows the conveyance of the different T30 messages back and forth from one end of the call to the other end of the call, and come up with a complete picture of what happened during this. So at that point, we are up to actually taking some questions. Steve, would you like to look at what we're getting for questions here and look to see what we're going to talk about?
Okay, great. Thank you, John. So just as a reminder, if you have any questions, there should be a questions panel in your GoToWebinar GUI that you could post questions to. So while the attendees are thinking about that, John, do you want to go through some of the some questions we may have, as far as basic questions that have risen in the past?
Sure. One of the most common questions that we get is, well, gee, this is all fascinating, but how does DataProbe manage to look at the IP data streams and figure out which call it is you're trying to look at? And that's one of the values of being able to take the analog portion of the call and compare it directly to the IP information, because DataProbe has a whole set of heuristics built into it that are designed to go in, look at the various aspects of the PSTN analog call, search through the different message streams that are recorded with the IP connection, and find the particular IP messages that correspond to those T30 messages. And at that point, it allows us to look at things like what was the DIS content, how many pages were sent, probably about a dozen other things, and come up with this right here, this SIP pipeline was the call connection that we recorded with the WAV file or with the data trap, and that's the one we need to be making our comparison with. Quite frankly, I have been a bit amazed myself at how well this works as we've gone out into customer facilities and plugged directly into their call exchanges and been able to insert a test call and have DataProbe watch the traffic going through a router and come back with, oh, okay, here's the IP information for that call. Impressed, if I do say so myself. Another question we have commonly received is, what's the distinction of IP G.711 calls versus the PSTN connection? Literally, what is the difference that happens between them that causes G.711 to sometimes not work so well as the PSTN connection? And again, this is largely a matter of what happens with the internet itself. G.711 is taking an analog continuous signal, and literally it is continuous. Fax is dependent upon probably a less than 5 millisecond variation of the timing and content of a call from one end of the connection to the other. What that means is that if you're taking the analog signal from a fax terminal, digitizing it, and putting it out as G.711 packets, and you lose one of those packets, then at that point the modulation symbol or symbols that were contained within those packets disappears from the call. And fax tolerates that very poorly. Again, it was designed for the PSTN, which doesn't have such issues unless you drop the connection itself, in which case you perforce have lost the call. The other thing that tends to be a bit of an issue is packet jitter. One of the things that, again, fax is sort of dependent on is this notion of having a continuous stream of analog data. And when you packetize it, send the packets to the other end, and they arrive at different times. Packet 1 will show up, packet 2 shows up, and then there's a wait, and then packet 3 and packet 4 show up, and then there's another long wait, and then packets 5, 6, 7, and 8 show up. That requires a buffer at the far end that is assembling these packets and presenting them continuously to the gateway to be integrated back into an analog signal that the other fax terminal can understand. This ability to buffer up these packets and present them continuously is called a jitter buffer. And jitter buffer tuning is one of the arts of fax over IP. I call it that because it tends to be a case of having a human individual tweaking the size of the buffer and the rate at which it is accessed to sit there and basically, okay, we're getting close, okay, that's the sweet spot right there. Let's operate it at that level. The other thing that happens with G.711 is if you have a badly misrouted packet, it's almost the same thing as a lost one, because if that packet shows up too far downstream in the transmission of the call, then there's no way to get it into the gateway to be integrated back into its proper place in the data stream. So the real issue with G.711 is the packet misroutings, losts, and being backed up in a jitter buffer where it can't be found.
John, I have some questions from the audience, so let me go through.
Good.
These. Okay, so let me ask the ones that are relevant, I think, to the topic of discussion that you're talking about right now. One question from Adrian. I presume DataProbe employs a de-jitter buffer implementation, so that's able to reconstruct and decode a packet stream. Is this configurable, i.e. needs to simulate the gateway?
We don't directly simulate the gateway. What we try to do is absorb all of the data that's going across and buffer it up to the point that we can take an entire call and reconstruct it. That is a bit of overkill from the gateway perspective, because what the gateway is trying to do is it's just trying to keep a continuous stream of packets going. What we're trying to do is we're trying to get as much information about that call as we can so that we have the maximum opportunity to reassemble it, to look at things like packets that are grossly out of sequence and flag those and say, hey, this will probably be a problem at the gateway end. But we're not trying to simulate what the gateway does. In many cases, we're trying to compensate for what the gateway does. That was not quite what you're looking for. Please re-ask the question in a little bit different terms, and we'll try that one again.
Okay, here's a couple of questions from Robin. Have you seen any failures due to bandwidth limitations? And if so, were they T30 or T38 failures?
Typically, you don't get into bandwidth issues with T38. It's really miserly with bandwidth. The big issue with bandwidth is G.711 because it will soak up a full voice channel worth of information, and in cases where bandwidth becomes an issue, you're winding up with too many G.711 calls. That business I talked about earlier of packet delay and misrouting and jitter issues becomes severe. And at some point, the bandwidth constraint will mean that the gateway at the other end just simply can't reintegrate the calls that are going through it in time to keep the timing requirements for T30 met for talking to the terminal itself. With T38, a greater issue than bandwidth is the problem of a lost packet. And T38 actually has a fairly robust methodology for dealing with that. It uses a redundancy system where the underlying transport layer, UDP-TL, actually sends redundant packets along with the regular call information packets. So the other gateway sits there and receives not only a continuous stream of T38 packets with T30 messages embodied in them, it also receives all these redundant packets. So if it's going down and saying, okay, there's 1, there's 2, hey, where's 3? Okay, it's came along with 4, so I'll just pull it back out of the batch for 4 and put it back in its proper place. So bandwidth with T38 typically is not so much of an issue as is lost packets, and it has compensation methods. Bandwidth for G.711, on the other hand, can be a real issue, and in a lot of cases, there are not real good solutions for it.
Okay, here's a question from Chris. Is it possible to combine the fax emulator, FaxLab, with T38 DataProbe, i.e. make a test with the emulator and have in the analysis also T38 data?
Absolutely. In point of fact, you can run both products on one host PC at the same time. It was intended to work that way. The beauty of doing something like that is that FaxLab gives you the capability to have an absolutely controlled fax call. Literally, FaxLab controls what happens on that call down to the millisecond and down to the 1/10 of a dB of signal level. So you're looking at a call that you know the parameters of at the T30 level, and then you can use DataProbe to go out and watch what goes on at the IP level and see, okay, what's happening with this, what's happening with that, what goes on when I send this kind of a fax call. One of the values of using something like FaxLab is the variety of T30 capabilities you can exercise. You can set up a call that's 3 pages, ECM v17 using MH encoding, and watch that happen. It goes through, well, that looks pretty good. Let's change encoding from MH to MMR. Run it through, and all of a sudden the thing goes to pot. What happened there? And you find out that, oh, well, our gateway over here doesn't do a good job with turning MMR encoding back into a signal that the answering fax terminal can understand. So yes, it is hugely useful to use DataProbe with FaxLab. And in point of fact, we're currently in the process of doing a consulting project with one of our customers doing just that thing. We're using FaxLab to probe their system and DataProbe to monitor all of the interactions within it.
Thank you, John. So let me call out to the audience one more chance for additional questions. So while people are thinking about that, let me take the control back and present the summary slide here. Okay, so as John explained, T38 DataProbe 3.0 version provides a really powerful analysis tool for T30, T38, and now G.711 encoded fax exchanges. In addition, FaxLab can be used to generate automated control fax calls, including T38 and G.711, by partnering with the voice over IP gateway or a analog telephone adapter. And our company provides fax testing service and training service that could assist your company with our in-depth fax expertise and analysis. And for those interested in purchasing any test tools that we discuss, we do have a new year promotion going on right now that's lasting through March 25th. And finally, we do have another webinar scheduled for tonight, 7 p.m. Pacific time, GMT -8, for any colleagues that have missed this one, or others you may know that may be interested in learning about this topic. So one last call for questions. So I'll give the audience a few more minutes. And then if you think of any follow-up questions after the webinar, please send them to info@QualityLogic.com, and we'll respond to those as quickly as possible. And we'll also make this, we recorded this webinar, so we'll make the recording available sometime later. So if you want to refresh your mind with any of the topics we discuss, there'll be a recording available for your convenience. Okay, so I don't see any more questions. So thank you again for everyone for attending this webinar. And again, if you have any follow-on questions, please send them over to info@QualityLogic.com. Thank you.